combinatorics. Well, before we start on combinatorics, just a word about factorial notation. The actual definition for a factorial is this. Now, I don't know whether you've seen it like this before, but that is what the definition is. It starts with 0 factorial, and 0 factorial is defined to be 1. And then to work out the next factorial, you simply multiply it. So n factorial, n times n minus 1 factorial means to work out 1 factorial, I would multiply 1 by 0 factorial. So again, the answer is 1. To get 2 factorial, I'd multiply 2 by 1 factorial. I'd get the answer 2. 3 factorial, I can keep going. 3 times 2 factorial. 4 is 4 times 3 factorial. And so on, and so on, and so on. Now, this means we can, what we call, roll out the factorials. So n factorial will end up being n times n minus 1 factorial, but then the n minus 1 factorial I could write as n minus 1 times n minus 2 factorial, and so on and so on and so on, and we could roll it all the way out to 1. And we'd simply end up with all of the numbers multiplied together up to n. So if I have something like 12 factorial on 9 factorial, and I didn't have my calculator in front of me, then I know, well, hang on, I can rewrite 12 factorial as 12 times 11 factorial, and I can write 11 factorial as 11 times 10 factorial, and I can write 10 factorial as 10 times 9 factorials. The 9 factorials now cancel, and I'm just left with 12 times 11 times 10, which is 1,320. So if I had something like 16 factorial and 10 factorial, 7 factorial, what I'm going to do is basically cancel the biggest factorial. So 10 factorial would be the biggest one I could put in the 16. I'm cancelling that out, which means on the top, I'm left with 16 times 15 times 14 times 13 times 12 times 11. 7 factorial is still on the bottom. So 7 times 6 times 5 times 4 times 3 times 2 times 1. And we should see a whole heap of cancelling. So I could go, oh, look, 7 twos are 14. Bango, that goes. So now I've got 16 times 15 times 13 times 12 times 11 on 6 times 5 times 4 times 3. But hang on, 5 threes are 15. So I can cancel those ones out. So I now have 16 times 13 times 12 times 11 on 6 times 4. But hang on, I could put the 6 into the 12, it goes 2 times. And the 4 into the 16, 4 times, and I end up with 4 times 13 times 2 times 11, which is the same as, well, I'll put the 13 and the 2 together, 4 times 26 times 11, that's 104 times 11, that's 1,144. Clearly, yes, it would be quicker to pull out a calculator and go, there's the answer. But we don't always have numbers. Sometimes it might be algebra, and so we need to know the technique of rolling out that factorial so we can cancel. Because if I got something like this, algebraic fraction, 1 on k factorial plus 1 on k minus 2 factorial, how am I going to do it? We need to get a common denominator. So my common denominator, well, if I rolled out the k factorial, I would have k times k minus 1 times k minus 2 factorial. Therefore, what have I left with? Well, the k minus 2 factorial, I've ended up multiplying by k times k minus 1. So the 1 on the top becomes k minus 1. So I have k squared minus k plus 1 over, well, I'll put it all together now, the denominator, over k factorial. Now, your calculator's not going to help you out on that. So that's why, as I say, we need to know the technique of rolling that factorial out. All right, let's move on to our look at combinatorics. And we always start with the basic counting principle. If one event can happen m different ways, then after that you've got another event that can happen n different ways, then the number of ways the two events can occur together is m times n. A simple idea. But why the idea is important is, you know, when we draw up tree diagrams and sample spaces and things like that, if they get large, it takes quite a bit of time. And the reality is, we're not actually interested in what's in the sample space. We're interested in how many things are in there. So really, I don't actually want to know what they all are, just how many there are. Because that then goes back to our probability formula, which is number of things in the event space over number of things in the sample space. So I can have a quick way of working that out without having to draw up the whole sample space. And it all comes from the basic counting idea. So if I roll 3 dice, How many ways can they fall? Well, I don't want to write out every possibility. That was okay when we had 2 dice. There were 36 different things to write down, but here I'm going to have 6 times 6 times 6. There's your basic counting principle, because the first die, 6 different things. Second one, 6 different things. Third one, 6 different things. And so by our basic counting principle, if all 3 are happening together, we get 6 times 6 times 6, which is 216, which would be a very large sample space that we would have to draw. So the number of ways of arranging n distinct objects with replacements, because essentially that's what I've just done there. I'm using the same sort of die each time, so it's like I'm replacing the die. Just because I rolled a 1 the first time doesn't mean I can't roll a 1 the second time. So it's like it's with replacements. Then it would simply be n to the power of k, because I'd end up going n times n times n times n. And so that can save us a bit of time too, if you think about it logically. How many ways can all 3 dice show the same number? Well, that'll be 6 times 1 times 1. So the way I would think about that is, I'd imagine I'm doing it, and I go, right, I'm going to roll the first die. It can be any number I like, so it's got 6 possibilities. I'm now going to roll the second one, but I want them all to have the same number, remember. So now, it's only got 1 possibility. I'm now going to roll the third one, I only got 1 possibility. So by the basic counting idea, 6 possibilities. This now lends ourselves to the logical question, what's the probability that all 3 dice show the same number? The number in the event space we just worked out was 6, over the number in the sample space is 216. So 6 over 216, we have a 1 in 36 chance of that happening. Let's have a look at this one from an HSC, yeah? This is quite an interesting one. So mice are placed in the centre of a maze. And this maze has 5 exits. Each mouse is equally likely to leave the maze through any of the 5 exits. And just to make sure you understand what that means, they've given us a little hint there. Thus, the probability of any given mouse leaving by a particular exit is 1 in 5. There are 4 mice, A, B, C and D. They're put into the maze and they behave independently. What's the probability that A, B, C and D all come out the same exits? Well, total number of possibilities, remember we said equally likely, would be 5 to the power of 4. The first mouse has got 5 to choose from. The second mouse has got 5 to choose from. So 5 to the power of 4, 625. But now how many ways going through the same door? So here's the mice, they're in there. Right, first mouse has 5 choices. Second mouse, 1 choice, because it wants to go through the same door. Third mouse, 1 chance. Fourth mouse, 1 chance. So all up, 5 chances. Thus, the probability that they all use the same exit is 5 in 625, simplifies down to be 1 in 125. And this is the thing with combinatorics. There are different ways of thinking about it. And sometimes you're just going to put working out down, and someone is going to look at this work and try and make sense. Now, if you get it right, it's not a huge issue. You get it wrong, someone's got to try and work out your logic to see whether there was anything behind it. So that's why I like to set it out, so I can explain my logic. This is why I'm putting down this, so they can see, all right, you might have screwed up in the answer, but your logic's sound. I'll give you something. All right, so the second part of this question was, what is the probability that A, B and C go out the same exit, D goes out a different one? So A, B and C use the same exit, D uses a different one. Well, I claim that's going to be 5 times 4 times 1 times 1. Here's my logic. D, I'm going to let go first. So D, 5 doors to choose from. Then the next mouse, whether it be A, B or C, they're all going to use the same door anyway. They now only have 4 choices because they're not going to go through the same door as D. But then, well, the other 2 have to go through the same door as the second mouse. So there's 1 way. So all up, there's 20 ways for them to leave our maze. So probability, 20 out of 625, 4 in 125. They then followed it up with this question. All right, well, what's the probability that any 3 of the 4 mice go out the same exit and the other comes out a different exit? See, in the last one, it was specifically D went out a different one and A, B and C went through the same one. Well, we just worked out the probability that D uses a different exit. Now remember, it's equally likely. Every mouse is equally likely. So logically, probability of A using a different exit must also be 4 in 125. Probability of B must also be 4 in 125. Probability of C must also be 4 in 125. So therefore, the probability that any mouse uses a different exit and the others go out the same would be 4 lots of 4 in 125, 16 in 125. So what's the probability that no more than 2 mice come out the same exit? No more than 2 mice. Well, no more is one of those trigger words again. It's like at least, no more. So you're thinking, are you giving me a hint here? Are you telling me I should think about the complements of this? What would the complement of no more than 2? Well, no more 2 would be they all use the same, or 3 use the same. And they're the 2 probabilities we just worked out. So it's 1 minus the probabilities that we have just worked out in our problem already. And so we get 108 in 125. Let's now talk about the specific type of situation that we call permutations. So a permutation is now when our objects are ordered. So it's an arrangement, if you like. So there's a specific order to the object. Let's look at some cases. I've got n different objects and I'm going to arrange them all. That's what they're basically saying. So I'm going to order n different objects from a group of n different objects. I'm going to use all the objects. So everything's going to be used. Okay, let's imagine those n objects are in the corner over here. And I want to get them, I'm just going to line them up out the front. Use the basic counting idea. How many objects have I got to choose from over here? N. So therefore there's n different ones I could choose to put first. Now I'm going to go get the second object. How many? N minus 1. Now I'm going to go back and get the third object. N minus 2. And so on and so on and so on. Eventually, and we get down to 1. Well, look at what we got. N times n minus 1 times n minus 2 all the way. There's our factorial that's been rolled out completely. So it's just simply n factorial. Let's now put some numbers into that. 5 boys, 4 girls. We're going to arrange in a line if there are no restrictions to how they line up. How many ways could we do it? Well, 5 boys, 4 girls, that's irrelevant. It's just 9 people. So 9 factorial. That's 362,880. What happens if we want to make the line look pretty? We're going to go, no. Let's alternate. How many ways of doing it? Always look after your restrictions first. Somewhere in this problem there's a restriction there. Something we're forced to do. If the boys and girls are alternating, I am forced to put a boy first. I have 5 boys and 4 girls. If I don't start with a boy, it will be impossible to alternate. So there's my hidden restriction with this one. So I look after that. So the number of ways, first is a boy goes first. There's one way of doing it. Only way I can start this line. Okay, well, seeing we're getting the boys, how about we just line up the boys? There's 5 factorial ways of doing that. And all we're now going to say is, look, do you want to just leave a space in between each of you guys? Because that's where the girls are going to go. So let's arrange the girls. 4 factorial. And we just slot them in the line. We have our arrangement. So 5 factorial times 4 factorial, 2,880 ways. Had there been the same number as boys and girls, then at the front, instead of saying 1, I would say 2, because I now have a choice. Will I start with a boy or will I start with a girl? So now the logical question from all of this, what's the probability that when they line up, the boys and girls alternate? Well, number in the event space over number in the sample space. 2,880 over 362,800. That's 1 in 126 ways of that happening. Now hang on. 2 girls, they're really great friends. They just want to be together. So forget about the alternating. 2 girls want to be together. Look after the restrictions first. So we'll arrange them first. There's 2 factorial ways of doing it. or 2 if you like, but 2 factorial, 2 objects, 2 factorial. Okay, brilliant. As far as we are now concerned, that little group of 2 girls are 1 person now, because their order now is not going to change. They're going to, it's like we tied them together, they can't, you know. So now, instead of arranging 9 objects, we're arranging 8 objects. That group of 2 girls that are tied together, and then the other 7. So 2 factorial, 8 factorial, 80,640. Okay, that was the situation where we used up every object. But what about if we don't? So we've still got our n objects, but we're only going to arrange k of them. And obviously k has to be less than n. So we're only going to use some of the objects. Well, let's do it the same way. Our objects are over here. We get the first one. There's n I can choose from. Then there's n minus 1. Then there's n minus 2. And we would keep going until we get to the kth object. This is now the last one I'm going to pick. The kth object. How many ways could I choose the kth object? Have a look at the pattern. When there was 1 object, it was n, or if you like, n minus 0. When there was 2 objects, there was n minus 1. When there was 3 objects, there was n minus 2. So logically, if there's k, n minus k plus 1. Well, that's a bit awkward trying to remember that, so we don't. We rewrite it like that, which looks, hang on, what are you doing? Are you insane? You've just made that look incredibly more difficult, but actually look closely what I've done. I'm just multiplying by 1. Right? The numerator and the denominator is the same. But now have a look at the numerator. n minus 1, n minus 2. I have rolled out the factorial all the way down to 1. Look at the denominator. I started at n minus k, rolled out the factorial all the way to 1. So really, it's now n factorial divided by n minus k factorial. There is a lovely button on your calculator that will work that out for you. The permutation button. NPK. So you don't even have to enter n factorial divided by n minus k factorial. You just have to go NPK. I think it's either on the multiplication or division key on a lot of calculators. Which one? Multiplication. So it's on your multiplication key. You use that one. But think about this. There's another way of thinking about it. N factorial divided by n minus k factorial. What have I done? N factorial is if I arrange every single object. Okay? But hang on. Over here, there's n minus k people that I didn't use. I didn't arrange them. So I divide by the number of ways I could have arranged the ones that I didn't use. It's another way of thinking about that formula. So I've divided by the number of ways arranging the objects I didn't use. Got the word problems. We want to make 5-letter words, and you see, fortunately this is maths, not English. And so any arrangement of letters is a word as far as we're concerned. You know, we could have smleb, blems, oblum, robble. There's all sorts of great words we can have. Okay, that's why sometimes you see it written not so much as letters of the word, they just say, oh, arrangement of the letters. But all right, no restrictions, we can go for our life, make any word we like. How many ways? 8p5. There are 8 letters in problems. We're going to use 5 of them. Now, you of course will go for your calculator and you'll get 6,720. If you didn't go for your calculator, it would be 8 factorial on 3 factorial, the number of ways of arranging the letters we did not use. So 8 factorial on 3 factorial. Well, the 3 factorial would cancel into the 8 factorial. When we rolled it out, we'd be left with 8 times 7 times 6 times 5 times 4. That would be exactly the same answer. Well, let's make it more fun than that. The word must begin with P. Always look after your restriction first. The word must begin with P. So we'll start off and place the P, and there's only one way we can do it. It has to be the first letter. So P goes first. Now I need another 4 letters, but you see, the question has now changed. It's now 7p4 because really what we're now saying is how many 4-letter words can we make out of roblums? So 7p4, 840. Now, let's mix it up a bit more. This time, P has to be in the word, but not at the beginning. It's not going at the beginning. And no, we don't like M today. We're not going to use M. M's excluded all up. Look after the condition first. P is included. So this time I'm going to place P, but there's only 4 spots I can put it. I can't put it in the first spot. So there's 4 places I can put the P. Now the other letters. 6P4. M is excluded. So now I'm making 4-letter words out of robbles. So 6P4. And that all works out to be 1,440. Okay. Just imagine, for this sort of probability question, if we had to write out the sample space. Write out every single possibility. All right, we're going boating. 6 people are in a boat. 8 seats, 4 spelled incredibly badly on each side. What's the probability that Bill and Ted are on the left side and Greg is on the right side? It's probability, so the first thing I'm going to work out is the sample space. How many is it out of? So no restrictions. There are 8 seats. We're going to end up using 6 of them. So 8P6. 8P6. And that works out to be 20,160 different ways these people could sit in the boat. Bill and Ted as our restriction. They've come up and said, we have to sit on the left-hand side. They now only have 4 seats to choose from. So it'll be 4, we're going to use up 2 of them, 4P2. So then Greg comes up and says, well, if they're going to be on the left-hand side, I want to be on the right-hand side. So Greg, okay, 4P1. We still have how many people to go? 3 people still need to be seated, and we've only got 5 seats left. 5P3. Multiply it all together, 2,880. But remember, this was a probability question, so we now say, well, the probability would be 2,880 out of 20,160, works out to be 1 in 7. There's a 1 in 7 chance that they could do that. I think it's the last example, but I thought I'd finish off with an HSC question. Sophia has 5 blocks. A red one, a blue one, a green one, a yellow one, and a white one. We're going to stack, or she's going to stack them up, 2, 3, 4, or 5, to form a tower. So 1 block by itself is not a tower. It's just a block. But as soon as you start stacking the blocks, you get a tower. How many different towers could she form that are 3 blocks high? And they're different colours, you see, so the way of arranging the blocks is different. That would be different towers. 5P3. There are 5 blocks. She's going to arrange 3 of them. 60 different towers. How many different towers in total? We just worked out the 3 block towers. But remember, we could have 2 block towers. 5P2. That's 20. We worked out 3 block towers, 60. 4 block towers, that turns out to be 120. 5 block towers, 5P5, which is also 120. Add them all together, we get 320 possible towers. All right, time to play.